Purdue University. And today he would be presenting his talk on the topic neural nets and numerical PDEs. A quick introduction about him. Professor Sai received his PhD in applied mathematics from the University of Colorado. His research interests include numerical solution of PDEs, iterative techniques in multi-level and domain decomposition methods for computational solids, fluid mechanics, and electromagnetics. He's also a visiting faculty at the Center of Applied Scientific Computing at Lawrence Livermore National Lab. So without any further delay, join me in welcoming Professor Sai. And Professor Sai, you can share your screen. You can go ahead with the presentation now. Thank you.
Okay. Well, thank you for the introduction. Thanks for George for the invitation. Actually, it's kind of nervous to give a talk in your group. Your group is a leading research group in scientific machine learning. So my talk is exactly what we were chat about is the more scientific machine learning. So basically, the title is the neural net. We basically using the neural network to solving the partial differential equations. This is my co-author, Zhen. She just graduated and now she's working for the Microsoft. And then Dr. Liu is from mechanical engineering. So let me give you the outline of my talk. How do I move? Okay. So basically, I talked about the two part of our research. One is we're using the neural net to solving the most nonlinear scalar hyperbolic conservation laws, or even other kind of PDEs too. Then when we're using this neural network instead of a finite element, then the same question is, how do we choose the architecture? So that's the reason the second part of my talk is about how to adaptively design a neural network for solving a given problems. Okay. So when we're talking about network, I guess I always have to give before I doing that, so let me give you a slide, sort of like describe what is the current state or the, so to me is instead of learning cat or dogs, so what I see from this field is more like a neural network give us a new class of simple functions. So we can use them to approximate complicated functions, the solution of the PDEs. And it's a common knowledge. Everybody probably think about neural net is very powerful in approximation. The current state, I believe, we still don't understand much about neural net, which is extremely powerful. Most of the people we're talking about is expressive power, but in how to use that is very difficult. The second part about a neural network is instead of create a linear space like piecewise polynomials, other well-known approximation function class. This one is a set. It's not a linear space. So that implies in order to solving that problem, we have to deal with non-convex optimization problems. Then this is the price we have to pay, and it's extremely expensive, and moreover, it's very uncertain. In the meaning of that is we even don't know what we converge to, because this kind of problem have many local and global minimums. Okay, so there are a lot of uncertainty here. Now, your group is probably the first one leading group to apply using the neural net to solving PDEs. So here, instead I'm writing that, I'm just saying this is a popular wisdom. Actually, a couple of them is probably from the talk from your group. Basically, you guys claim that is, at this moment, this kind of approach is not competitive for lower dimensional PDEs and for the forward PDEs. And also, some of you researchers claim that is very competitive for inverse problems. Now, of course, a common motivation for people study the neural net is because of this high dimensional PDEs, right? So this is a high dimensional PDE. This is one of the most motivations. In my view, I'm more thinking about it's too early to make any kind of either positive or negative conclusion on the application of neural net. So in my talk, I'm basically trying to show that we are able to construct some very competitive neural network scheme for the lower order, for low dimensional PDs. Okay, so but this requires a lot of understanding for the neural nets and requires a lot of the well thought out the design sense. Okay, so let me first give you one slide. Since we're talking about neural net, and neural net is basically popularized by machine learning sense, or more supervised learning. Well, so I put a title here is really this kind of machine learning. If you're talking about supervised learning, this is really a data fitting or a glorified data fitting, right? I guess this is the glory of this machine learning or curve fitting is because of the neural net, the powerful approximation property of the neural net. Now, I want to say a few words about this is supervised learning or machine learning sense. There are two aspects of that. One is, of course, is from a statistic point of view. So the problem they are looking at is more for a given and data, which is very limited. Moreover, the data is noisy. Then they're talking about that this kind of problem have studied for 200 years, right? And then, of course, the current applications, you have a new ingredients like a neural net as a model, and then plus the data is in a high dimensional space, etc. So for my research, I'm more focused on the other aspect of this machine learning, which is the approximation theory. So we want to use the neural net to approximate a function, or most importantly, we want to approximate a solution of PDEs. So when we're talking about approximation, then the problem is very, very different. So here, instead, we are given a set of data. So our data is unlimited. So we always think about behind of that, we have a function or a solution. So, and also the data is not noisy. But the challenge in here is the data is not given, but we have to find right data in order to approximate that function or solution accurately. Okay, so that's the one I want to say a few words on this. So if you think about when I'm looking at the machine learning or the data science, really a lot of that work is just the curve fitting in a way. Okay. So now let me give you one slide for the neural network. Everybody knows what that is. I'm just specified. We're not looking at any fancy network. We're only looking at very classic, fully connected, or called the multi-layer perceptrons. So let me just using that. So as a class of function, there are a lot of research going on, but still, I'm more thinking about we probably don't understand this class of function very well. Now, of course, one of the well-cited result is a universal approximation theorem. If you think about other class of approximation function, universal approximation theorem basically is a dense theorem, right? So basically say this is a function, this class of function is rich enough to approximate the function you want to do. So this is, from approximation point of view, this is basically a minimum requirement. So here I listed, instead of its multi-layer neural net, I write a two-layer. So because we're trying to have some understanding. Now, of course, recently there are a lot of research about what is the convergence rate, the error estimate, etc. So let me don't mention much about that because all this kind of research are very important and very interesting, but in somehow when we apply to for applications, when we're looking at a problem, interesting problems, all this theorem is not easy to apply because of naturally, this is kind of asymptotic result. And then when you're doing the a priori estimate, then you have some unknown quantities. And moreover, you assume that the function clause has a lot of assumptions on that. For example, if you're looking at the reasonable result on the barren space, then it's very interesting. But when you're looking at the solution of PDEs, you basically you can validate the solution of PDEs belongs to a barren space. I think Wei-Lan Yi and his collaborator wrote in some paper on that. So when we use this one for solving PDE, one of the key question is, well, before we are using neural net, we already have several class of functions. And this kind of research has been done for like 50 or 70 years. It's very well established. So the first question we want to ask in that is why should we use the neural net for solving PDEs? So the past 2 years, our work is based on this observation. If you're looking at two-layer neural net, so this is much easier to understand. As I write in here, every function looks like the following. It's a linear compilation of sort of like a basis function, one, and this is sort of like a basis functions. If the omega I and the bi are fixed, then this is exactly one of the fixed basis functions. But a neural net and omega I and the bi's are the degree of freedom are the parameters to be determined. So that is one of the reasons why the neural net is so powerful in the approximations. If you're looking at the history of the approximation theory, in a one-dimensional case, this is identical to what people call free nut. So finite element basically is a fixed nut. You have a fixed partition, then you construct the piecewise polynomials. And if you let your partition move, then that's what they call the free nut. But only since they only can do the one dimension. So I was so excited about this neural net is a simple formulation. They can generate this free nut to any dimension. Okay. So then if you're looking at history in the 70s and 80s, people already know that free nut spline in one dimension is much more powerful than finite element or the fixed nut spline. So that's one of the reasons that there are a lot of good properties. So that's the reason we're trying to use that to solving PDE. Okay, so now let's look at the PDE. Because this neural net is not a linear space, so we cannot do the discretization in the traditional way, which means we cannot be writing down the same number of equations with the same number of unknowns. Because the dimension has no meaning here. So instead, we have to rewrite our problem in terms of minimization problems. So let's look at the PDE. So we have many different forms of the PDE. Now, of course, what we see usually is the strong form, the differential equations, right? So since if we want to use the neural net, we cannot use that equation. So one way we can write that is for some a small class of PDE, there is an underlying minimization principle. So we can write this one as equivalent to minimize energy functionals. So this is what we usually call this is a risk method, right? The risk formulations. Then for most of the PDE, we don't have the minimization principle. So anything is non-symmetric, then you don't have a minimization principle for that. So that's the reason people apply the least square principle to the PDEs. So this is actually the least square formulation for the PDE actually is a subfield of finite element. And there are a lot of research was going on. Actually, I myself spent like 80 years in the 90s, in the early 90s to the early 2000, working on the least square formulations. Actually, at that time, I was very excited. The first time when I went to the Lawrence Livermore lab, so we were excited, McCormick and Manteuffel, we were so excited, we were trying to convince the people to use in finite element. After a couple of years try, then we're never a success, because first of all, the problem in the lab is so complicated, and the second sense is what we learned is they never want you anything what you do shouldn't be intrusive, which means you cannot touch their discretization schemes. But anyway, so let me explain what is the least square formulations. Most of the work on the least square is for the elliptic problems, for the elasticity and for the fluid problems. So let me use a simple second order elliptic problem to explain this Ricci field. There are a lot of work on that. Even right now, I was not very, probably since the early 2005, then I was not actively working on this field, but since 2013, we still have like a biannual workshop on this topic. Okay, so this is the general second order elliptic partial differential equations. Because of this is a convection term, so this problem is non-symmetric. There's no minimization principle of that. So the first least square formulation is due to the Bramble and Schartz. This is the work before the pre-finite element era. At that time, before that, people basically using the finite difference to discretize the PDE. Then when the boundary is a curve and how to impose the Dirichlet boundary condition is very difficult. So that's the reason they introduced this least square formulations. So basically what they do is they just apply the least square to the original equation. That's what you see from here. Now, and then the boundary condition, Dirichlet and the Neumann. But one thing I want to make point out is for the equation, they use the L2 norm. For the boundary conditions for Dirichlet, in order to make this a least square, every term is balanced from mathematical point of view. The strength for that should be the 3/2 derivatives. And similarly, for the Neumann boundary condition, you already have one derivative here. So this is 1/2. So this is a well-balanced least square formulations. As I say that the reason they did that is for the how to impose the Dirichlet boundary condition at that time. Now, one thing let me point out is in this formulation, we have to require our solution has to be sufficiently smooth. Otherwise, this formulation does not apply. Now, of course, when the solution is smooth, then a lot of numerical approach works well for this problems, right? So this is the reason in the 80s, then people start thinking about, can we develop some least square formulation that works for more general, can apply to the general class of problems. That's the reason then people think about ideal from ODE. If you solve in a higher order ODE, one way to doing that is you introduce the additional independent variable that you can reduce the higher order ODE to the first order system. So that's the reason for this one. If we introduce what we call the flux, this actually has a physical meanings. Then we can write the second order equation, this equilibrium equation as the first order, the divergence of the flux, then plus the first order derivatives. Moreover, you can observe that this quantity, the gradient of u is curve free. So if you apply the curve of that, then this one is also equal to 0, even though this is you have more equations than unknowns, but they are consistent. And similarly, you can get additional boundary conditions. So based on this first order system, there are a lot of work about the squares. Let me just mention that is in the 85, then is there what they call the inverse norm sense, and also Bramble in the middle of the 90s did the inverse sense. And then we did something what we call the divergence least square method. We just basically apply to this formulations. And then if you apply the least square to the whole system, that's what we call deep curve systems, etc. Let me give you a simple introduction for the deep method, which is my favorite. in a way. So if we apply the simple least square to that province, this is the least square functional we're to minimize. And you can write in down the corresponding variational formulation. And also you can establish the coercivity continuities, which are important for PDEs, right? Then about 2 years ago, we write a paper about the neural network. At that time, we didn't know the pin, so we didn't sign the pin. But basically, when we apply using the neural net, so one sense about the neural net, the difference between the neural net and the finite element is it's not easy to enforce the boundary conditions. So instead, so we basically just adding to the functionals. That's what we did. Again, the norm is very different. So this is the half norm. This is negative half norm. Okay. Then you can do proof of allotticence. So when we write in this paper in about 2019, we didn't know the pin. And also we did some numeric experiment. At that time, we have very less experience about the all this kind of sense. Each for a one-dimensional problem, even very simple, which take like 20 hours to train. So this is the limit on showing that. But at least at that time, what we observed that is the this kind of approach does not give us the GIP phenomenon for the interface problems. So that's the reason we kind of was even that we see the potential of this approach. Okay. The second sense, the one thing that let me mention that is the as I mentioned before, is that when we talking about approximation, so we're not given the sampling point. So basically, you can choose any sampling point you want, but we want to choose the sampling point which guarantee our approximation accuracy. So this is a theorem basically says if you do the standard quadrature and using the right quadrature point, then you still have the error estimate in terms of the approximation property of the neural nets, then plus the numerical the error from the numerical integration. Okay. So let me the main sense for the past year, I think it's more than a year. Our main focus is on the hyperbolic conservation law. This is the basically this one type of problem we think about is most of the challenge in the numerical PDE, right? In this computational science and engineering. Now, the reason for that is the solution of this problem is discontinuous. Moreover, we don't know the location of discontinuities. So that just make the approximation is so difficult. Now, of course, the second part of this difficulty is the differential equation does not well describe the physical phenomena. So that sense you have to. So before I look at that, let's look at linear problems. This is probably when we're looking at the scalar conservation law, the first sense we always study the linear advection and reaction problems. I rewrite that a little bit and basically writing that this is the directional derivative along the direction beta. And the beta could be a constant vector or could be the vector valued function of the space and time. Okay. So for the hyperbolic conservation law, very few work about least square because the one reason that is the when we're doing the least square, our theoretical background is a Sobolev space, all the Sobolev series. And for hyperbolic conservation law, we don't have that. So that's one of the main reason, very, very few, probably I can count as less than 10 papers in this field. But for the linear problems, actually, least square is well established. So if we simply apply the least square, so this is the L2 norm for the equation. And for the, so instead I say this, the inflow boundary conditions, initial data, because we always compute in the bounded domain. So instead I call that the inflow boundary conditions. Okay. So this one is also L2. Okay. and only depends on the inflow boundary part. This is very important. If you're looking at it for the elliptic problems, we have a very, very different scale. Moreover, we can establish what is very important in the theory. This is the homogeneous of this least square functional is continuous and also is cursive. So which means if cursive, then that means that this system is stable. Okay, this is the main work by the Manteuffel and McCormick's group. At that time, so they are my main collaborator in the least square, but at that time I'm moving to the elasticity and the Navier-Stokes equations. But anyway, so this is we have a very solid theory behind that. Okay. So then we apply instead we're using the least square, using the finite element, we're using the neural net. So you can simply just minimize that least square in the class of the neural net functions. So this is neural net functions. Then you can easily establish what we call the quasi-optimal approximation. Basically says the approximation in this class is the best if you don't care about that the constant in the front. Okay, so that is important. Moreover, if you knew the solution structure of the problems, for example, for this linear problem, if your direction is a constant, then you knew that solution. If your initial data, if your inflow boundary condition is discontinuous, then you knew that your solution structure. So that's the reason we also prove this type of result is very interesting. Is if the solution is a piecewise constant, and also the Zhang is a constant along the interface, then what we can show that the neural net approximation is bounded by something depends on the approximation property, and U hat is the continuous part of the U. Then for the discontinuous part of that this is the Zhang, then epsilon is any positive numbers.
Can I ask a question on
yes.
the norms? Maybe
yes.
The triple vertical, like how are the norms are defined?
Oh, the norm is basically same if you let data equal to 0, right? Data equal to 0, so that's the norm.
No, not that norm. That when your notation, yeah, when you have like 3 vertical lines.
So that norm is the L2 norm of the directional derivative plus the L2 norm of the. So this is very strong norm.
Yeah.
But makes sense. Makes sense because this one makes sense. The derivative of the v does not make sense. The gradient does not make sense, but the directional derivative makes sense. So that is for this linear problem. We basically understand everything, and also we are using the right norm. Thanks. Okay. So this one basically says if U hat is in this space, then this term is equal to 0, then this is the accuracy. So if you're looking at that, so let's looking at the numeric examples. So this is our recent JCP paper just appeared, I don't know when. And this is a famous problem when everybody talking about a scalar conservation law, I guess particularly in the Brown. Professor Godlib probably spent a lot of time for this problems. Just UT plus UX equal to 0.
Yes, we call that the Godlib equation at Brown.
Oh, I see. Okay. we have a joke about that. This is the model problem for the scalar conservation law. Then the Laplace equation is the model problem for elliptic equations. And Seymour Potter is my friend. We write several papers on the least square. So one of his favorite joke is his wife after 40 years marriage, and when his wife looking at his work and say, after 40 years, you're still working on this problem? Just there, I guess it's there. Okay, so for this problem is one of the simple test problem is if we have the, as you can see that, this is the characteristic directions along the diagonal, right? So this part are the inflow boundary condition. And if the initial data or inflow boundary data is discontinuous, for example, 1 and 0, then the solution will be 1 and 0 here, right? 1 and 0 here. So as you can see that this is extremely a simple structure, but somehow if you're looking at all the mesh-based numerical schemes are very, very complicated. And because the solution is discontinuous, so even that, so you even have this oscillation, overshooting at oscillation sets. Even you use, if you don't taking care of your discretization scheme, even you use the adaptive mesh refinement, you still have this GIP phenomenon. So this is the, we just using that from this is a paper, 2002 paper, 2020 paper on that. So in that paper, they basically say, when you discretize that, you have to take in care. If you do something, then they don't have that. Okay, so let me show you what we have. So we basically using the 2-layer neural net with only 6 neurons. Okay, for this problem. And what do you see that this is the exact solution? Then if you're looking at this is a trace at interface, it's almost a perfect match. So here, what I'm trying to say is and we're using the standard training, using the Adams training, we only need 6 neurons. In a theory, actually in this case, we only need 2 neurons in order to approximate this function. This is a solution extremely well. Okay, so I just want to say that is this is very different from the supervised learning, because in order to compute this solution, remember that all the information is transported from this inflow boundary 0, 1. So they propagate along that. If you do the supervised learning, that's almost trivial. Okay. Now, of course, you were asking that theoretically we prove that we only need 2 neurons, but in the computation we need 6 neurons. This is the difficulty from that optimization, non-convex optimizations. Okay, let me show you when we published this paper, one review. Think about, this is a UT plus UX is too simple. So they give us some more challenging problems. So the profile more looks like you have 2 discontinuities, right? And then there are 2 discontinuities, and you have some more complicated functions. Still, in the same sense, we can approximate that extremely well. Since this is the trace, as you can see, that approximate discontinuous solutions extremely well. And one sense I didn't talk about that is this is what we call the break lines. Okay, so that break line match up with that discontinuous interface extremely well. For this problem, we did use in the 2-layer ReLU neural network with 31 neurons. Okay. Now let me show you one more example. This is interesting. So the velocity field is a piecewise constant instead of a constant. In this case, if we're using the two layers, no matter how many neurons we have, so here we're using 200, our approximation is terrible. As you can see, that's smeared. And even for that, it's not very accurate. And if you're looking at the location of all these neurons, this is the break lines, what we have. So you can see a little bit, this is the interface, a little bit, but does not line up very well. Instead, if we're using the 3 layer with 5 neurons at each layer, then we get almost a perfect solution. Then if you're looking at the how they capture this is Zhang, they capture extremely well. And if you're looking at break lines, that just perfectly line up with that interface. So this is a sense get us very, very excited about this neural net. Okay, so let me move to the nonlinear hyperbolic conservation law. If you have any questions, then I can answer you. Otherwise, I'll move into the. Okay. Now, this is the scalar nonlinear hyperbolic conservation law. So because we're computed in the computational bounded domain, so that's the reason we also add in the influ boundary conditions, right? You have the truncate, somewhere you have added that. So there are a couple of the least square papers on that. One thing is, no matter what is this data is continuous or discontinuous. This problem always have a discontinuities. For example, if that's what they call the shock formation, right? And so that's where we don't know where's the discontinuity. Now, for the linear problem, we do know. Now, of course, when you develop any kind of numeric scheme, you don't want to use it. If you use it, it's almost useless for this hyperbolic conservation law, right? Because when we develop the numeric scheme, we want that works for the nonlinear problem. Okay. So for this one, the second, so in the linear case, we basically showing that neural network is so powerful, they can deal with the discontinuity. So this is one thing in this field, one of the major difficulties, keep people away from that. So if you're looking at all this scheme, they're trying to develop that is like, we know all this kind of sense, they're trying to approximate that sense only using one side of grid point, right? That's the second difficulty for this one is the differential equation is not enough. Okay, so this is the one much more deeper. So that's the reason then there are very few least square formulation for that. Manteuffel group write a couple of that. So basically, ideal is they trying to introduce a spatial flux and trying to as an independent variable, then trying to enforce that the RH condition. But anyway, so our approach is basically still apply the simple least square. So this is the least square for the equation. Then we have the influ boundary conditions. Then we have initial conditions. Okay, so this is the our first paper is already on the archive. The second paper we probably put in on the archive in a couple of weeks. We submit to the GCP. Okay, so let me give you the what is our numeric sense. For this type of problem, the first test problem, of course, is the Berger equations. And the easiest Berger equation is a Riemann problem. So in that case, we have the initial is a piecewise constant. So this is we have the velocity speed on the left is 1, on the right is 0. So in this Riemann problem, then the shock formed at t equal to 0. So that's the reason immediately you have that sense. So if you're looking at our simulations, we're using the 3 layer with a very few neurons, even for that case, it's 10-10. Then this computation is almost perfect. We never see that. I knew that George wrote a paper about the apply the pin to the Berger's equations, but it's the visit Berger equations because the pin, from my understanding, is probably cannot handle the discontinuity. Maybe I'm wrong. So after the talk, we can discuss that. And also I see the one of the Peanuts paper also did the visit Berger equation, so which means the in that case the solution is a smooth, it's a continuous, it's smooth. Okay. This is a Riemann problem with a shock. Now, of course, we have to looking at the Riemann problem. If the speed on the left is less than the speed on the right, then that's a problem, what we call the rarefaction wave. Okay. So again, as what you see that this is a problem doing extremely well. This is actually a very interesting problem. My field was not the hyperbolic conservation law, even though for 20 years, I always like to working on this problem because in my view, from physical point of view, hyperbolic scalar conservation law actually is simpler than Navier-Stokes equations because the hyperbolic conservation law is a first order approximation and the Navier-Stokes equation is a second order approximations. But anyway, so this is very interesting in a way is for this a rarefaction wave. So if let me draw in that. So if I'm looking at this is the time, this is a space. So if we have the speed is less than that, right? So right is going this way, and left is going this way. Sorry that. So what you see is the following. This part is empty. There's no equation to describe that. Now it's really amazing in the 60s or even earlier than that. This is famous people, Peter Lax, Wendroff, they find a way that is apparently, if we're looking at here, this is a modeling issue, right? It's not the numerical issue, but they find a way of that, introduce the entropy and etc. They can compute this solution very well. So to me, it's the solution is not unique, and how do you fill up this part? Then now, of course, the mathematical term is you're trying to fill up with the viscosity vanishes solutions, which means you introduce a second order with a viscosity approach to zero. So hopefully you get the same solution on that part. So, well, basically our numerical schemes, we don't need to do anything. We still can compute this extremely well, compute the right physical solutions. Okay. So this is for the Berger equations. Oh, there are one more examples. When the initial data is more complicated.
Can I ask a question?
Yeah. Yes.
So like the entropy condition, how do we know that it is satisfied with a neural network?
Okay, that is, we basically ignore that. There is a conjecture when you're talking about the theorist. So viscosity vanishes solutions. So if even you're looking at all the mesh-based numerical scheme, basically there are two groups. One is they're trying to enforce entropy, right? Trying to use all this entropy condition to help you to design some schemes. The other one ignored. Now, of course, when you ignore it, then why that work? That's the question. So at least for scalar hyperbolic conservation law, there's some either conjecture or some understanding that is, if you can preserve the continuity of your numerical solutions, then you should get a right solution. So one way to explain that is because our approximate solution is continuous. That guarantee we have that, but not always that's true though.
Right. So in that sense, then the comment that you made about pins is, which is true. We also have continuous solutions. It's the same thing, right? Right.
But looking at pin has what's the main difference? We didn't call it pin because we didn't know that. If otherwise we would have used the pin. Pin is much more.
No, it's fine. But I'm saying that's because there's
a big difference. There's a big difference. The pin basically, you guys, if I'm from my understanding, you use automatic differentiation for the derivative.
Yes.
Is that correct?
Yes, correct.
Okay, so this is the main issue. When we doing the linear problems, we did the same sense. Then we get garbage out. We cannot observe that. We basically cannot learn that function at all. So the discretization of the differential operator is extremely important. If you think about what is automatic differentiation, I don't know that well. My guess is you basically approximate. It's sort of like a numerical type approximation along the coordinate direction. Is that right, George?
Well, we have different versions, but I mean, because we look at similar. We haven't published this, but we had a project for DARPA, so we looked at similar, exactly what you're doing. And we try different, of course, least square, but the L1 norm, for example, we try L1 norm, minimize with respect to L1 norm, and we get good results. The problem is L1 is not very easy to train, so we switch to L2, yeah. But I was just wanted to mention that some people at Sandia, for example, they try to enforce the entropy condition explicitly.
Yes.
And at least in 1D they show good results, but then the question is, it's not clear. It was incomplete conclusions. That's why I asked you the question, actually.
That's very interesting. L1, we need to talk more about that. This is very interesting. As the main sense, if you use an L2, we knew that is the automatic differentiation does not work. Or I shouldn't make that a broad claim. I should say that is let's do the numeric differentiation. If we do the numeric differentiation along the coordinate directions, we knew that does not work. Automatic differentiation may be doing a different sense. So my guess is that maybe just to differentiate the neural net functions. That we have spent a lot of time to think about, but we don't have much experience. If you guys like to chat about that, interesting to know what is exactly automatic differentiation do, and how to figure out a way doing the right sense.
We have actually a bunch of results. We could offline we could share at another time. Yeah, I don't want to.
That would be great. I'd love to. Yeah. Okay. Oh, sorry. So this is the rarefaction waves. We don't know that. So how to enforce the entropy? I don't know. What we basically believe the continuity would give us that, and then of course plus the if you're doing sense right about differentiation, that to us is the key. This is the much more complicated initial data. We in our new paper, we basically developed a new finite volume scheme. That finite volume scheme is very different from the rho, and we know. We think about it's much more suitable for the neural network. So when we use the rho and one more sense I want that. When we use the rho, for this one probably is a good sense for George to know that. When we using the differentiation using the rho scheme, then that fails for this rarefaction wave. This is probably a well-known fact in the numeric hyperbolic conservation law communities. The rho scheme does not work for the rarefaction wave. And now, of course, have a different type, and with a type similar to the rho, even its higher order does not work. Okay, just want to mention that. Okay. For the smooth data, when we use rho and it works, but not very accurate. in the part which is, this is not too small to see, in a minimum and a maximum part usually does not approximate well. So in our new schemes, which we can approximate extremely well, I just want to say that. Now, of course, because the solution is much more complicated, so the size of the network is much bigger. Okay, 30 by 30. But it still, when we compare our work with the most of work in the machine learning, then this is just too small, right? But this is the main purpose. We want to get a very, very small. So eventually, we can compete with the mesh-based. Eventually, I don't know how long, because we still have that bottleneck, how to solve that problem. So once we're done with the Berg equation, then the natural sense we want to do the other convex flaws. So the next step is the fourth order, higher order, fourth order, sixth order, etc. So this one, we probably cannot see the picture is so slow. Basically, all this simulation is our new finite volume scheme, but we have different. It's not order, some kind of a class, a family of that. Then for some lower family, inaccurate family, then as you can see, that approximation is not even that. If you're looking at this picture, is not bad, but if you zoom in, actually doesn't look that good. But actually, the error is very, very small, and as you can see, that is monotone, and there's no oscillations. But if you use using higher order, then this one we present 3 different orders. The highest order is almost perfect matchup. So that's a different at a different time. Then again, as you can see that because this is a solution structure, actually is very simple. So we're using a very small size of network. Then once we've done that, of course, the next one we have to do some non-convex. This is probably since comes in with the entropy sense, right? Entropy, if it's usually it works for all the convex flux, but for non-convex flux, then the story is much more complicated. So here is what we have, that even for that, we're using the higher order sense. Then if you're looking at numerics, it's unbelievable to me. Now, in this is experiment, we did using the same structure. Only problem with that is the one sense I didn't talk about, that is when we do the non-convex optimization, when we training that, we're using atom. If you're looking at most of the work, is they always suggest the random initializations. Our group is basically, in some way, we don't like it because for each round, we don't know what we get. And then I don't know how people report. Now I knew that the first paper we report is that we run like 5 times, then we report the best result we have. Even that was not great. So that's the sense in our work, we spend a lot of time on the how to initialize the iterative solvers. Now, for this is a 3-layer neural network, we knew how to initialize parameters in the first layer, but we don't know how to do the second layer. We know how to do the third layer, output layers. So that's the reason in this running that we ran the 10 times, 9 times is perfect. Okay, so we do have 1 time, it's not that good. But if you're looking at, if you don't zoom in, this is not that bad. If you zoom in, you can see a little bit the error. So I just want to make that as the for the cubic. At least so far, we haven't seen any numeric schemes for this is a scalar conservation law. Okay. Oh boy, I think I'm probably used all of my time. Let me just say one more thing: is all this is the architecture of a neural network is empirical. So we basically experiment based on our experience. We choosing that. That's about a year ago we already started that. Is the asking ourselves questions. If you give a problem, even a given function or given a PDE, how do we design an architecture the smartest possible to solving that problem? So unfortunately, I already used all.
Professor Kai, we are actually interested in this, so go ahead and you can use more time, no problem, because this is really of interest to us. Also the first part, but definitely I want you to go over this.
Okay. I guess you have the flexibility of that. Okay. So this is the sense of what are we talking about. So let me write in that. If I write in a neural network approximation, basically we want to find a solution. They minimize some kind of a functional, right? If it's the approximate a given function, we just minimize the L2 norm of that. The function is given. If we're solving the PDE, we're minimize that the square functionals or the energy functionals, no matter what that is. So a fundamental question is, for a given tolerance, okay, now this is, I guess most of the audience here has an engineering background. When I'm talking about in the math community, I always have to explain that. When we write in the epsilon in the mathematics community, epsilon is always means so small, 10 to the minus 16, machine epsilon, etc. But that's not what the computation about. In particularly, the George has a lot of connection in the lab. I spent all the summers in the Lawrence Livermore lab. So when you're talking to those people, the epsilon we're talking about is 0.1%, 0.5%, depends on the province. So for that kind of tolerance, and the question is, how can we design a smallest possible neural network such that in some kind of measurement, of course, measurement is always difficult, such that this is true in the relative errors, right? It's less than the quantities. So if you're looking at a mesh-based method, we do have a subfield in the finite. We call the adaptive mesh refinement or the posterior error estimation. We're trying to address that issue, right? For neural net, it's much harder because the neural net is quite new to us. There are a lot of sense we don't understand. This is a sense there are a lot of people trying to understand the sense. One sense I want to say that is the standard a priori estimate. Most of them does not give us any understanding. So this is one sense is the even my background is more mathematical, more theoretic oriented. I always question that because of my lab experience. I always question that what we proved does not explain the phenomenon, the computational phenomenon. That's a pity. In a way, is our mathematician, we trying to use our mathematical tool to understand the sense and trying to provide some explanation of the phenomenon from the computations. Unfortunately, we don't. Now, of course, that's also, you can see that this is the limitation of the mathematical theory, because the mathematical theory, in generally speaking, is more asymptotic in nature. You start from the calculus, the core of the computation, the core of applied math is approximation theory. And approximation theory in the nature is asymptotic. So that doesn't help much. But anyway, so in order to address this problem, the ideal is basically very, very similar to the adaptive mesh refinement. That's the reason when I was spent in lab, I failed to convince the people using this square. So this other part is I was excited about the neural network is my least square expertise can be used. But at that time, so I basically gave up the least square, then moving on to do the posterior error estimation and the adaptive mesh refinement. In particular, at that time, because the DOE was talking about the predictable computation. So that's the one part of that. Now, of course, George was the leading figure and lead all this predictable computation to the uncertainty quantification sense. I'm much more in the deterministic side. I want to, when we have that computations, I want to classify or quantify what is the error and trying to see whether or not we have a predictable accuracy. So that's basically what is the posterior error estimation about. So in terms of that, so how do we construct that? So as I said, ideal is very similar. So basically is in this kind of a 3-stage. If you're looking at the adaptive finite element, they write in the 4th stage, but essentially it's fine, 3-stage. Now I changed the terminology. Instead of solve, I explained to the train, because we never, even for the finite element, they never solve, but they almost solve exactly. But here, to solve exactly, that's almost a hope or a dream, right? We cannot do that because when we train, we even don't know where we are. Okay, then the second step, once we have approximation on the current, using the current neural network, then we want to estimate how good we are. Is our approximation good enough? Then we can stop. If our approximation is not good enough, then we need to change our model. In this case, we need to add neurons, right? So that's the reason we call it enhancement. So we're going to add some neurons. So this one actually we started more than a year ago, year and a half ago. This is because I spent the 80 years on this posterior error estimations and sense, because my lab experience realized most of the difficult problems we have to do the adaptive measure refinement. We have to have some stopping criteria like posterior error estimation to tell us whether or not our solution is good enough. Okay, so we write a couple of papers. All these papers on arXiv. So it's not easy to looking at multi-layer neural network. So we wrote the 2 papers on the 2 layers. It's much easier to that. So let me explain that. Okay. So before I do that, now for the finite element, the most difficult part is estimated part. So that was the reason most of research is about the posterior error estimation, because in particular for PDE, we don't know the solution. So if you don't know the solution, how do you know the error? So that's we developed a very powerful machinery to doing that. There are several things. Okay. In 4 or 5 years ago, with the Randy Bank from UCSD and Furfus from Germany, we organized the Oberwaffe conference. This is a self-adaptive numeric method for computational challenging problems. But anyway, so here we're looking at this neural net. So for finite element, this is the most difficult part. And now this kind of sense, a lot of them has been addressed by the finite element. Now, of course, when we're doing the neural net, there's some new sense comes in and a lot of new problems that we still have to deal with that. But if we're using the least square, so more or less, this becomes an easy problems. Okay. Then, so what is the difficult part? The difficult part is enhancement strategy. If my current neural network is not large enough for the given problems, how do I develop a strategy to enhance that? So this is the key question to answer. To do that, so let me explain that what is in the 2-layer, because multi-layer is much more difficult. Again, it's because our lack of understanding. Okay, so 2-layer, we basically understand almost, I wouldn't say all everything, but we understand a lot. Okay, so here their main question is, as I said, that when this one is not enough, how many neurons we can add? Because it's 2-layer, so I don't worry about which layer. I only need to worry about in the current layer how many neurons we need to add. And so we have 2 strategies. One is global strategy. So this is different from the adaptive measure refinement, because if you're looking at the neural net is the more like a global phenomenon, right? So in a way, I can just do in the global enhancement. So basically, we have a formula to compute that based based on what we know that is the error estimation at the current one and the one before that. So we're using that information to give us some rate of convergence. And then we can come up with this one. So here I want to say that is we basically don't want to add too much of neurons. We just want the each time we want to double, at the most double that. Okay, so just in that way, then we can make this is the increase of the speed of increasing is slower. So this is our global strategy step. So in that way, I believe it's much easier to use, and also this one I can apply to a lot of applications in the machine learning because we don't need much. Of course, one thing is, do you have estimator? In generally, if you use the loss functions, you use the least squares, then this is not a big issue. Now, of course, if you're using the rates, then that becomes an issue. And then, but again, as I say that, there are a lot of machinery from the finite we can use. Our favorite one, or the at least at the current state, it really works one is our local enhancement strategy. So this one is basically the number of neurons at the new neural network is something plus, this is what we're going to add. So this sense really depends on the local informations. That depends on the what we introduce a terminology, the physical partition. Okay. So I will keep using the example to explain what that is. If you think about that, is the if you're using ReLU, even though we don't have underlying the partition like a finite element, but we do have that. Okay. In a way. So once we have the enhancement strategy, then you can rewrite this one as an algorithm. Basically, you just start with a relatively small neural network. Then gradually you go through this procedure, right? So that's basically what the, so the key part is the estimator is good. Then you have a good enhancement strategy. So let me show you the, I guess before I show you the numerics, I should give you the one of the slides. As I say, that is the neural network is so powerful. I'm so excited because in my whole career, I was always pay attention about approximations. We have all kind of different class of functions. We have a polynomials. Then in the 60s, we have a spline. Then in the 70s, from 1D to the multi-dimension, then we have a finite element, basically it's a piecewise polynomials. Then of course we have the Fourier series trigonometric functions. We have the wavelet, we have a rational, all kind of things. But somehow I really like the neural net. Just the, it's still, we don't have a lot of things we don't understand. That's probably the reason why we need to do a lot of research. Okay. So the first hour, I give you a list. Hopefully I convince you that is the for the scalar hyperbolic conservation law, the neural net have a lot offer. As basically, in my own thinking is, I think the neural net is a holy grail for the scalar hyperbolic conservation law. This is the reason even I was a postdoc at Crown. So
Professor Kai, you have because now we have to finish up for the other talk, but you have the results for this. It would be nice to show the enhancement results because that's the
yeah. So let me finish up. Let me start.
No, we want to see the results. The results that
you want a result
with enhancement,
okay.
Yeah.
Okay. So the first thing is learning this is simple functions. What you see that is the from this table, you see that we started with the 10 neurons. Then we enhanced by adding 3, then we add in 7. Now, of course, it's based on this is the first sense, just the initialization. Then once you train, you get a very good approximation. Then you enhanced by following procedure, we compute the local errors. This red one is the 3 of the region we need the refine. If you're looking at that terminologies, we add 3 neurons in the right place. give us the right initializations. Then
is that on all layers, or on which layers do you do that?
This is only 2 layers. This
Oh,
is
we have 2 layers only. Yeah. Okay.
This is 2 layers.
Sure.
Yeah, and then this is a 20. Then we get this is a so if you're looking at this as a comparison, if we're using the fixed, this is adaptive, and if you're looking at even the numbers, it's much better, right? So this is more trendy neurons kind of works as similar as the accuracy of the third aid, because the optimizations, you never know what you do, right? So this approach basically gives us the exact deterministic approach. This one, instead of just learning the function, we're learning the solution of PDEs. This is a one-dimensional Poisson equation. I believe we learned this, we using this example is from Wei-Lan Yi's paper and the Jin-Chia Shu's paper, the first paper, that did extremely well. But of course, when you're doing the PDE, then we need more neurons. Instead of 20, we have 25, okay? Because the solving PDE is much harder, right? We have, because we're using the reads, we have the estimator, so let me don't skip that. And also we did this one for the L shape. We have this as a, as you can see, this is the exact solution. This is what we learned. And for this L shape, we only need the 86 neurons. If you compare with the, even for this elliptic problems, compare with the number of degree of freedom, it's much, much less. If you're looking at the mesh refinement, that's a huge number. Now, of course, we pay a huge price. I just don't want to. This is the adaptive process. So we started with this one, and then we find where we need to refine, we need to add, then we add that. This is the final one. Okay. This is a Kellogg problem. This is one of the really difficult benchmark test problems for the adaptive finite element. We did extremely well too. So, so let me stop. So I want to give you the information. The message you take away is the neural net is extremely powerful. We don't know much. So far, at least our group only using one sense is basically the that feature I sense about the free not spline features. And the price to pay is extremely high. Okay, so this is the very, very, very difficult. Our approach is basically trying to provide the good initializations that keep us at. For the application, the hyperbolic problem, I believe this is a great approach. So, and then this is our sense about adaptive neural network. I should stop here. I'm using too much time.
Thank you very much. Thank you.
Thank you.
Thank you, Professor Tsai. Any questions for Professor Tsai? If we have no more questions, Professor, I have one question which I wanted to ask you is, how do you decide the initial number of neurons when you talk about adaptive neural network?
Well, start as small as possible.
Okay. So is there any way, like if my initial number of neurons is high, is there any, do I get any error estimation which says that I need to reduce my number of neurons?
Okay, this is in a finite element, we call that a coarsening process. Yes. If you have, okay, this is not easy to address. The main thing is the training procedure. We know nothing, right? It's basically what do you know? Now when you're using the larger one, most likely you trap in some local minimum. So you could try just the remove some neurons hopefully you can jump out of that then doing the adaptive procedures.
Okay. Thank you, Professor. Is there any more questions from anyone? So if there are no questions, let's thank Professor Sai for the wonderful talk. So thank you so much. We can now move to our second speaker.
Let me stop share. 1 second. Okay.
So our next speaker today is a member from the Crunch group. He's Zhen. So today he would be presenting his recently submitted article on GFINNs, which is Generic Formalism Informed Neural Network for Deterministic and Stochastic Dynamical Systems. So yeah, you can share your screens in.
Oh. Can you see my screen?
Yes.
Okay. So hello everyone. Today I'm going to present a recent work that is in its preprint now, called GFINNs, Generic Formalism Informed Neural Networks for Deterministic and Stochastic Systems. And this is a joint work with Dr. Zhang and Professor George Kaniadakis. And yeah, let me begin. So to start with, let me first describe the problem that we are considering. So this is the general problem we're considering is the data-driven discovery of dynamics. Basically, what we want to do is we assume that we have the input to the problem is some sort of time series data, and we assume that it is there is some kind of governing equation which is responsible for generating this sort of data. And the governing equation could either be deterministic or stochastic. And in general, there are two major approaches to infer the dynamics from the time series data and further extrapolation. These two approaches are, one of them is the pure data-driven approach, and the other is commonly referred to as the physics-informed data-driven. Basically, we assume that we not only know the time series data, but we also know some specific physics information that is driving the governing, driving this time series. And in order to take these physics into account, normally there are two approaches. One is the soft constraint. One is to use the soft constraint, and another is to use the hard constraint. By soft constraint, I mean we place the physics as part of the loss function and do the back propagation from that modified loss function. And by hard constraint, I mean we directly encode the physics knowledge into the neural networks. And through the hard constraints, normally we can sometimes we can achieve better results because the physics principle are encoded in a more explicit and strict way. So next, let me give the problem formulation. We assume that we have the time series data sampled from the following ODE. Z dot equals to f zt, where z is lies on open set in RD, and t goes from 0 to t, and it starts from initial condition z0. And our goal is to infer f from the data for z given as z tj z0k. So which means that these are the trajectories of this time series sampled at time tj and starting from k different initial conditions. And many methods have been proposed to address the problem above. and there are like traditional approaches and the neural network based approaches. And some traditional approach, including works by Professor Nathan Cruz. I think he proposed a method called Cindy, which is commonly used in this area. And basically, the key idea is to propose a surrogate model f theta for the right-hand side of the equation, and then optimize the model with respect to the parameter theta using the loss function given as below. And the loss function is defined to be the mean value of the difference between v theta, zj, z0k, and ztj, z0k, where ztj, z0k is the ground truth theta value, and z theta is computed by applying a numerical integrator, applying a one-step numerical integrator, starting from a ground truth value to get the next value using the using the surrogate model z dot equals to f theta. And by propagating this loss function with respect to the parameter, we can get an approximation for the ground truth f. And with that, we can further extrapolate in time, or like generalize the equation on other initial conditions. And one common approach that is used for such task is the neural ODE. Basically, what they do is like they just parameterize the right-hand side f as a standard feed-forward neural network. And for this approach, the only model assumption is that basically the system is deterministic, and there is no other model assumption. So we can see it as some sort of purely data-driven approach. And there is another approach. There is another method called the Hamiltonian neural network, where it assumes that the right-hand side of the equation takes a specific form. Basically, it assumes that the data is generated from a Hamiltonian equation. And what they do to handle this specific type of data is that they also parameterize the neural network to reflect that. And what they do is they parameterize the right-hand side of the equation to be equals to J inverse gradient of HNN, where HNN is a standard feed-forward neural network. And by this kind of parameterization and using the loss function in the previous page, they can learn better from the data generated by the Hamiltonian equation. And that is for data which is from the Hamiltonian equation and which is conservative. And for some data which is in general dissipative, there is a recent work called the Onsager network, where they propose to model the right-hand side of the equation using the specific form of m plus w times gradient v, excuse me, plus f. And so here the m and w, one of them is antisymmetric and another of them is positive semi-definite. And by this formulation, they in general incorporate the Onsager principle into the neural network, and as a result, they can learn some dissipative system from data. And so our approach is, and our goal here is also to learn from some general dynamical system, which could in general be dissipative or irreversible. And we want to incorporate the so-called generic formalism into the neural network through the hard constraint. And so what is a generic formalism? Basically, a generic formalism takes the form of z dot equals to L times dE dz plus m ds dz. And it has to satisfy some specific degeneracy or consistency conditions, in the sense that L times ds dz should be equals to m dE dz equals to 0, and L has to be skew symmetric while m has to be symmetric, positive, semi-definite. And here the E is the energy of the system, while S is the entropy of the system. And L is called the Poisson matrix, and M is called the friction matrix. And this formalism is specifically useful because it can be used to describe beyond equilibrium thermodynamic systems, and it can be used in the modeling of complex fluids. And here, the L dE dz accounts for the reversible phenomena of the system, and this term is equivalent to the Poisson's equation of motion. So if we don't have this part and we only have d dot equals to L times dE dz, then we recover the general Poisson system from classical mechanics. And the second part accounts for the irreversible material properties of the system. And this term is motivated by the Ginsburg-Landau equation, which can be used to describe critical dynamics of spatially extended systems. And what we want to do is like we want to assume that we have data generated from this specific type of ODE, and we want to recover the dynamics from the data, and we want to construct neural networks for L, E, M, and S, so that the corresponding functions will strictly satisfy this sort of degeneracy conditions. So to convince you that this generic formalism is important, there are two simple theorems, basically saying that if we assume that our state variable z is generated from the generic formalism, then we will automatically have the first and second law of thermodynamics, in the sense that dE dt will be equals to 0, while the ds dt will always be larger than or equal to 0. And so actually there has already been 2 works which is focusing on utilizing the generic formalism in the data-driven discovery of dynamics. And one of the first work is called the structure preserving neural network. And what they do is like they assume that in the generic formalism, they assume that L and M are known, and they parameterize the dE dz and ds dz as neural networks. And they penalize the degeneracy conditions through soft constraints. And in some circumstances, this will lead to some bad results because these soft constraints can be violated. And further, we need to tune the weight of this soft constraint compared to the loss for the ODE. And to tune the parameter, it is time-consuming work. And another approach is called the generic neural ODE, which is done by Professor Dr. Nat Trask in PNL. And what they do is like they parameterize the right-hand side of the equation through some bracket notation. And actually, this work is done just a few months ago, and our work shares some similarity with this one, but they have some sort of implicit modeling assumption, in the sense that when we write the detailed form of it, we find that they implicitly assume that the generator L is a linear function of ds dz, and M is a quadratic function of each component of dE dz, which may not in general hold. So in general, if that kind of implicit model assumption holds, then of course their neural network or the generic neural ODE will achieve a good result. But if such assumption doesn't work, then they cannot have the desirable predictive performance. And this is one of their issue, and we overcome this sort of issue by proving some sort of universal approximation theorem of our neural network, so that in general our neural network can be used to infer and extrapolate from almost arbitrary dynamical systems. Arbitrary data that is generated from a generic dynamical system. And our approach is to parameterize the right-hand side of the equation, L dEdz plus M dsdz. We parameterize each part of these four L, E, M, and S as a neural network. We consider three different scenarios. The first scenario is where we assume that L and M are known, and the goal is to approximate the energy and entropy through the neural networks. And case 2A is where we assume that E and S are known, and the goal is to approximate the generator L and M. And the case 2B is we assume that everything is unknown, and the goal is to approximate the four of them. And yeah, this is a general graph illustration of what we are doing. We start from the data for Z, which is a state variable, and we propose some orthogonal modules through the neural networks to parameterize dEdz, M, dsdz, and L, which we by our design of neural network, we automatically ensure that dEdz is orthogonal to M and dsdz is orthogonal to L, meaning that M is dEdz is in the kernel of M, and dsdz is in the kernel of L. And we design the loss function using the MSE loss, basically between the Zj and one-step integrator applied on Zg minus 1. And here are the three scenarios that we are considering. And the biggest problem that we encounter is that we have to strictly satisfy this orthogonal condition. We want to design neural networks that this strictly holds. So we somehow take extract the question to be the following. We assume that A is a d by d matrix valued function, while G is a real valued or scalar valued function whose gradient is in the kernel of A. And we want to develop strategies to parameterize G in terms of A and parameterize A in terms of G. So we want to design a neural network whose gradient lies in the kernel of a specific matrix valued function. That is case 1. And case 2 is we want to design a matrix valued function whose kernel contains the gradient of the specific function G. And yes, that is the problem we are considering. Basically here, the A will be the L and M in the generic formalism, and this G will be the E and S in the generic formalism. So because there is this kind of symmetry, like so we just use A for both L and M, G for both E and S. And so in case 1, we first put some modeling assumption in general, and we will later show that this assumption holds in all of our test cases. And these are not very strong assumptions in general. So this assumption is a standard assumption that is commonly applied since the 1970s, and typically to make the analysis through. So because we need this assumption to prove the universality theorems, basically saying that we want the kernel of the A, which is L and M, to have some sort of constant rank. And we also assume that the largest subspace of kernel A, whose rank can be represented by the span of some basis function, satisfy some invariance properties, in the sense that we want the range of the Jacobian of these basis function to lie in the kernel of the matrix A. And The second assumption we made is that we want to have some we'll assume that there is some auxiliary function fj, which like whose gradient is constitute the another part of the kernel of A, and we assume that the span of the gradient of f together with the previous space we introduced, the direct sum of these two parts will constitute the whole kernel space of matrix A. And we design our neural network so we first define a projection function, which is defined to be q times d concatenated with fa of d, where qa of d is composed of the basis function qaj, and the fa is the auxiliary function we introduced in the second assumption. And to concatenate with them, we actually know that the gradient of this projection function will automatically lie in the kernel of A. That's the design. That's why we want to design this projection operator. And by applying a neural network F on this projection function, we get our neural network design for the matrix G or the matrix E and S. And by the chain rule, since the gradient of this projection function lies in the kernel of A, like the gradient of E and S will also automatically lie in the kernel of A. And we actually proved one of a universal approximation theorem, in the sense that we define A to be we define FA to be the collection of differentiable functions G, whose gradient satisfies gradient G takes this form of Jacobian PA transpose times CA composite with the projection composite with PAZ for some continuous function CA. And this function space may look suspicious at the first glance, but it is generally enough to represent arbitrary function whose gradient lies in kernel A if A is a constant function, meaning that it is not a function of Z. So it is in general actually a large enough function space. And we show that our neural network is actually universal in that function space, in the sense that suppose A is a d by d matrix valued function, and we get that for any G defined through our neural network parameterization. Assume that G lies in the function space FA, then there exists a neural network model GNN such that the L infinity norm between the gradient G and gradient GNN is less than epsilon, and also the gradient of GNN lies in the null space of A. Yeah, and that is for case one. In case two, we are considering like the other way around. So we, here we, sorry. For case two, we are assuming that we don't know anything about L, M, E, and S in the generic formalism. So as I previously said, like in case 2A, we actually assume that we know the E, the energy and the entropy, but we want to formulate the problem in the more general setting where we don't assume anything. And the case 2A, where we assume something, can be easily can be seen as a subclass of this problem. So here we just assume that we don't know anything, and we let Sj to propose our neural network architecture. Let me begin with the lemma. So let Sj to be a skew symmetric matrix of size d by d, where d is the dimension of the state variable z, and for a differentiable scalar function g, let Qg be a matrix valued function whose jth row is defined to be Sj times gradient g transpose. then we will automatically have like QG gradient GX is equal to 0. Basically, this says that when we have a function form for G, we can design a function QG, whose kernel contains gradient G. However, if we use this QG directly as our choice for L and M, for example, we have the energy function E for this G, and we use this we use the QE directly as our candidate for L, who has to be orthogonal to gradient E. It's not going to be satisfactory because there is another condition in the generic formalism, like here, saying that L has to be skew symmetric. And through that, and if we just parameterize L as QE, then this kind of condition will not be satisfied. So we need to add another term through the spectral decomposition theory from linear algebra, in the sense that we parameterize A to be equals to QG transpose times BA times QG, where if we want A to be skew symmetric, then we parameterize BA as a skew symmetric matrix, like here. We parameterize it as the difference between two triangular matrix valued functions. And here, TL is also a neural network. And if we want A to be positive semi-definite, then we can parameterize it to be the product between TM and TM transpose and TM, where TM is also a triangular matrix valued function. And this kind of parameterization, for this kind of parameterization, BL can represent in general arbitrary matrix valued function, which is antisymmetric, and BM can represent arbitrary matrix valued function, which is positive semi-definite. And also A will automatically be either skew symmetric or positive semi-definite, while its kernel will contain gradient of G at the same time. So, and we also prove a universal approximation theorem, in the sense that we suppose that gradient GNN is accurate enough so that it is actually equal to gradient G, where G is the approximation target, like the energy and entropy in the generic formalism. And a component of gradient G has non-zero values in the whole space. And we let A to be either skew symmetric or symmetric positive semi-definite matrix valued continuous function, satisfying that A times gradient G is equal to 0. Then for any epsilon, there will exist a neural network model A that is defined that can be defined before, such that it is close enough to the approximation target A in terms of the L infinity norm. And also the degeneracy condition A times gradient G will be equal to 0 automatically. So do you have any question at this point? Okay, yeah, let me continue. So basically, up to now, we have defined two different neural network architecture to handle two different scenarios, and both utilizing the generic formalism for the data-driven discovery of dynamics. And so here is another thing. Basically, the generic formalism can be extended also to the stochastic differential equations, in the sense that so this is the stochastic form of the generic formalism, in the sense that it can be written as dz dt equals to mu z dt plus sigma z dwt, while the mu takes the form of ld dz plus mds dz plus kb divergence of m. So if we take the limit of kb goes to 0, then this is essentially the same as the deterministic system or deterministic generic formalism we discussed before. And this is a natural extension of that into the stochastic systems. And the degenerate conditions are basically the same, while the only difference is that they add another condition called basically the sigma times sigma transpose is equal to 2kb times m, where this formula actually guarantees the fluctuation dissipation theorem. Yes, so this line is just the fluctuation dissipation theorem. And so we can also do the data-driven discovery on this stochastic system, in the sense that we assume that we have data generated from this SDE, and we can utilize this kind of formalism and to learn both mu and sigma. The way we do it is just the same as before. I mean, exactly the same as before, by parameterizing mu as the neural network constituted by L, E, M, and S, which automatically satisfies the orthogonal condition. And we parameterize sigma to be equals to the square root of m divided by some constant because of the fluctuation dissipation theorem. And through our parameterization of this m of this m matrix, we find that it is a square root through Cholesky decomposition can be automatically obtained through the Tm times QENN, where Tm is the triangular matrix that we discussed before. And because this is a stochastic differential equation, the loss function has to be designed in a different way, in the sense that we utilize the loss function from a recent paper of Yannis. So we use a maximum likelihood estimator to design this loss function, in the sense that we calculate the probability of djk given dj minus 1k, where the probability distribution is can be calculated from the one-step Euler-Maruyama discretization of the previous SDE, and so through that we get that this PZJK given dj minus 1k will be the density function of a multivariate normal distribution with the mean delta tj mu nn and the covariance matrix 2kb delta tj mnn. So this loss function can be easily implemented in PyTorch. And so these are all the methodology we are utilizing. So in summary, we propose a method which can work both on deterministic and stochastic ODEs, and can handle two different scenarios where we know L and M, or we don't know any one of them. So, and the two approaches are not the same. So we first test our method on a gas container example, where we assume that we have the state with the state variable is given by Q, P, S1, and S2. And we have a gas container, like in the middle, there is a wall that can be pushed left or to right. And in each gas container, there is some gas, and so not in the thermodynamics equilibrium, and the wall in the middle will move left and right in an oscillator way, and this function is actually very nonlinear, so not easy to learn, and so this is so it can be formulated in the generic formalism directly, where the L, E, where the L, M, and S matrix can be given in the L and M matrix can be given in the following way. And we simulate 80 trajectories starting from t equals to 0 to t equals to 8 with delta t equals to 0.02, and use 20 trajectories as test data. And we compare the performance of our method with the structure preserving neural network, which use the soft constraint in case 1, where we assume that L and M are known, and we compare our method with the generic neural ODE. In case 2A and case 2B, where case 2A is we assume that we know the energy and entropy. Case 2B is that we don't know energy and entropy. And it turns out that in all the 10 experiments, our method can achieve a better results for this gas container example. So that our conclusion is that because of the expressivity of the neural network, because of the universal approximation theorem, the method can, our method can actually is actually better in terms of the generalization, because the training data and test data are from different, starting from different initial conditions. And here we plot the learned energy and entropy of the gas container example by the GFINN. So if you look at the top left, so this is the ground truth value of the energy contour at the hyperplane S1 equals to 2.5 and S2 equals to 2.5, and this is the contour for the entropy at P equals to 0 and Q equals to 1. And it turns out that after some calibration procedure, in both case 1 and case 2B, our model is able to recover the correct contour, energy and entropy contour in the for this gas container example. And also, we test that whether the generic formalism is, the first and second law of thermodynamics is strictly enforced through our parameterization. And we find that it is indeed the case in the sense that we calculate the dE/dt and ds dt, where E and S are not here, it is not the ground truth, but our neural network. And it turns out that on this, for this neural network, the dE/dt will be equal to 0, and ds dt will strictly be greater than or equal to 0 in this gas container example. And we also tested our results on a more difficult thermoelastic double pendulum example, which is in general chaotic. And basically we achieved a similar result, showing that our method can achieve a lower minimum max MSE compared to its counterpart with soft penalty or the GNODE. And finally, we test our method on this Langevin equation, who has the simple energy form of P squared over 2 plus S, and like the L and M matrix also take a simple form. And it turns out that this Langevin equation can also be written in the generic formalism with this given E, L, M, and E and S. And we simulate 40 trajectories for training. And note that this is actually very small data because this is a SDE and we only have 40 trajectories. And the initial conditions are randomly sampled And to evaluate the predictive performance of the model, we sample another 50,000 initial conditions from the same distribution and solve the SDE using the learned drift and diffusion term with the Euler-Maruyama method. And we apply the Gaussian kernel density estimator to approximate the distribution of V and ZNN at time steps t equals to 0, 0.5, 1, and 2. Note that the training data are only from 0 to 1. So the result for t equals to 2 actually corresponding to the extrapolation in time. And this table shows that for our method and the SDE net basically this SDE net is the method which parameterizes the mu and sigma as neural networks directly instead of putting generic formalism into them and using the log likelihood estimator also. So that one doesn't use any physics knowledge in general. So by incorporating physics knowledge into the neural network, we see that the training, even though the training loss is similar in all of our 3 cases of our method and that data-driven method. The prediction error, for the prediction error, there is a very big difference in the sense that by our method can achieve a better result than the SDNet because we incorporate more physics knowledge. And here the prediction error is calculated in terms of the squared sliced versus type 2 distance by comparing the distribution of the function z at time t equals to 0.5 and t equals to 1. So one conclusion is that by incorporating the physics, we can achieve a better prediction error. And another conclusion is that in case 1, case 2a, the prediction error is smaller because we assume that we know more things in the sense that we know, in case 1, we know the L and M matrix, while in case 2a, we know the energy and entropy of the function. And in this slide,
sorry to interrupt, Zhen. You may want to plug in your charger.
Oh yeah.
Sorry. Oh yeah. Sorry.
Thank you. Give me like 1 second. Yeah. Okay. Yeah. Thank you. So, yeah. So let me continue. And so this is the plot that we have, basically drawing the kernel density estimation of the function z at different time steps, where the yellow line is the density at t equals to 0. The blue line is the density at t equals to 0.5, and red line is t equals to 1. Green line is extrapolation in time, meaning t equals to t. And we can see that in case 1 and case 2a, where E and S are known, the neural network is doing a good job in the sense that it can recover it can learn the distribution well. While in case 2b and SDNet, there is the density estimation is not as good, but still, like in case 2b, the result is slightly better in the sense that at the like t equals to 0 and t equals to 0.5, it matches the ground truth pretty well. So that's all of our results, and our next step will be like using an autoencoder to handle systems in high dimensions, because we realize that for our approaches, if the state variable z is in a high dimension, then there could be some problem because like we need a lot of parameters to train, and the training will be specifically slow. So that's why we want to use an autoencoder to map the original state variable to a lower dimensional space, and maybe apply the GFINN on the latent space, and then use a decoder to map it back to the original space. And another issue is that here we assume that we have the 4 observable of the function z in the generic formalism. So here you can see that. But here you can see that this is the generic formalism, and we assume that we have every variable in this z. And in general, this assumption may not hold, and sometimes maybe we need like a change of variable or add some hidden variables to make these to make the model assumptions to relax in some sense the model assumptions. And that can also be achieved through some sort of autoencoder type of techniques. And that is what we are going to pursue in the next step. And that's it. And I'm welcome to any comments or questions.
Do we have questions for Zhen? So if there are no questions, we could actually end our seminar for today. So let's thank both the speakers, Professor Kai and Zhen. So thank you. And Zhen, you can stop sharing your screen. So thank you everyone for this week's seminar, and hope to see you all soon. Have a good weekend. Bye.